I guess yesterday's lecture is quite fresh in our minds so far, so I don't think we need to have any recap or anything. But just very quickly, we discussed k-means, we discussed hierarchical agglomerative clustering, and we discussed db-scan. 3 different algorithms, 2 of the most basic ones, and then the db-scan, which is a little bit more advanced and more interesting in my opinion. And now the question is, how should you know which one is working better than the other, right? I can very easily tell you that you will never know for sure because it's very hard. But anyway, there are ways that you can check that, especially if you're running a benchmark, even though it's not perfect, but you can. And one thing that usually people think is, well, you know, every clustering technique has its own kind of like a measure in a way, because for example, k-means you're optimizing for the intra-cluster variance, so you can check for that. And but these things there, and there are other things that you could do, but the problem is that if you take one measure for each algorithm, like how can you compare them? Like how can I compare the output of a k-means and the output of db-scan in a way that, like an external judge, like using an external judge, someone who looks at the clustering and say, okay, for this data set, without considering any of your own internal measurements, actually db-scan doesn't have that, so that wouldn't even work, but some of them has. So the external judge is the one that says, okay, no matter which kind of a target you were trying to optimize, I will evaluate the results in the same way, independently. And that's what cluster validation or cluster quality measures are about. So that's those few questions arise. How can we check if they're good partitions? How can we compare? And how can we find good parameter settings? So this is also an important part. How can we find good parameter settings by comparing different results? Because for example, let's say I have no idea how to set the epsilon. I have no idea how to set the minimum points parameters. And then maybe you can, for example, run it like 20 times and then you have 20 results. And then the next question is, okay, how do I find which of these 20 results were best? With k-means, you can use just their internal metrics, but not with the db-scan, for example. So one way is comparing to the ground truth. This is what we call external validation. And basically it's external validation because you have some form of labels in this case. So we're considering that you have that. And you can say, well, you know, in real life, unsupervised techniques, unsupervised, let's say, processes, you don't have the labels. So you can't do this, period, right? So in those cases, you won't be able to do this because you need the labels for this specific measurement. But on the other hand, if you are like developing a new algorithm, for example, or developing an improvement over a previous algorithm, then this could be used as a testing phase for this technique that you're developing, right? So then at this point, you can use techniques with labels, and then as soon as you're comfortable and you think that, yeah, you know, the technique is working nicely, then you use it for unsupervised things without really checking too much if it's good or not, because then you kind of assume it's good because you tested it before. So, and the idea here is that you have a set of ground truth classes, so just labels, then you have a set of clusters, and then you have these 3 measurements here, the number or the set of points where 2 points are in the same cluster and in the same class. Then they go into this pair, the pair of xi and xj, they go into this set of ss. Then sd are pairs of points that are in the same cluster but not in the same class. And pairs of points, DS is a pair of points that are in the same class but not in the same cluster. Now, one thing that is important to remember here, whenever you're going to use any kind of external validation for clusters, is that even though you have classes and you may have the same number, let's say I have 3 classes in my data set, I know them. I know the labels for my points, and there are 3 classes. Even if you take 3 clusters, and this is a very interesting thing, even if you run k-means and get 3 clusters, there is no guarantee that these clusters that you got, the 3 clusters that you got, are actually equivalent to the 3 classes that you got. And even worse, you don't know which cluster is related to which class. That's the problem, actually. There's no one-to-one connection between a cluster and a class, such that you can say, okay, cluster number 1 is related to class number 2, and cluster number 2 is related to class number 1, and so on. So you don't have this connection. You have 3 classes and you have 3 clusters, and they may or may not have the same elements, right? And that's why you need to kind of like work around this by considering pairs of points. So you take a pair of points and you say, okay, these 2 guys, are they in the same cluster? Yes. Are they in the same class? Yes. So they go, so this pair, not the points, the pair of points goes into SS. And then take the next pair of points. Again, are they in the same cluster? Yes. Are they in the same class? No. So they go to another bucket, SD, and so on and so forth. And then after you did this for every pair of points, then you compute this Jacquard coefficient, which is basically the number of points that are in the same cluster and same class, divided by the sum of all of them. Well, not all of them, because you may have, there's an extra one here where the two points are not in the same cluster and also not in the same class. So in the same, so this is not, I mean, these are the stuff that we are considering here. Comparing to ground truth. External validation also. This is purity. Again, another one, right? This is one, and this is another one. This is actually, I think, a little bit, well, both of them are quite common. And it's still, here we're still using labels. So again, it's still a little bit, let's say, limited, I say, because you don't always have labels. But anyway, in order to compute purity, you have to, so you have this, to compute this maximum, this maximum intersection between a certain cluster K with a certain class J. So you compare the class, take like a class, like class 1 that you have, whatever it is. Then you compare this with all the other clusters, all the other clusters, all clusters, CK, and count the number of elements in their intersection, and then choose the largest one. So in this case, what we're doing is we're trying to actually determine some one-to-one connection between a class and a cluster, right? Actually, it's not one-to-one. Is it one-to-one? It's not necessarily one-to-one, because you're doing this for each cluster, right? So for each cluster K. Now, there is no, let's say, guarantee here that you will have different clusters connected to different classes. So it may be that maybe some clusters will share the same class because some weird result where 2 clusters are related to the same class, for example. So you take for each cluster, then you consider the class. You consider the cluster K, find the largest intersection, and then you use that one. And this is an interesting result that will actually you will actually understand why I mentioned that. For example, let's say cluster 1. Cluster 1 is connected, the largest intersection is between cluster 1 and P. I don't know, I don't remember why they use P here instead of just labels. Right? I mean, maybe it's because C was already taken. So C1 has the largest intersection with P4. So then in this sense, we kind of consider like, yeah, okay, if I had to guess, I would say that cluster 1 is more connected to the label 4 or class 4 than anything else. It still has, you know, it still has some connections to every class. So there are 3 points in common between cluster 1 and class 1. There are 5 points between cluster 1 and class 2, and even 96 for cluster 1 and class 5. So it's not a perfect connection. But given that we have to choose one, then we will choose this one because it's the largest one. And then you do the same for every cluster. So cluster 2 is connected to class 3, cluster 3 is connected to class 6, cluster 4 is connected to class 2, cluster 5 is connected to class 1. And then when we come to cluster 6, you can see that cluster 6 is again connected to class 1. So we have this class number 5 here that has not been like picked by any cluster. So for some reason, we didn't find any cluster that was strongly connected with class 5, while we found 2 clusters that were strongly connected with class 2. So that may be counterintuitive, but that's just how it is, because the external labels, when they come, you never know. I mean, they're just external labels, right? You can't necessarily connect it to, like, it is definitely connected with this cluster or with that cluster or so on. So so sometimes you extract patterns from the data, and then you realize that these patterns, they don't necessarily match the classes that you have, because of whatever, I don't know, because of how the data set's too complex, or because the labels that you have extracted are actually not that representative, not as representative as you thought they were. Who knows? But anyway, that can happen. And this is how you compute purity. Then you take these values like 506, 286, 7, and so on, and then just sum them and divide them by n, the total of number of points, right? And then you get something like 0.72. The perfect thing here would be if every cluster was connected to every class, to each class, like one by one, and that they were perfect. So there was no other point shared with any other class, for example. Then you would get 100%. In this case, you get like 0.72, which is 72% of purity. Who knows? As an absolute value, it may not mean too much, but it will mean when you actually comparing. So if you do this for many different results, then you can compare them and say, yeah, this one has the highest purity, and so on. So again, it's a way to kind of like test the quality of the actual algorithms, because you need labels for that. Or maybe you have another application that you don't need labels, that you have labels, and that actually makes sense. Who knows? Maybe you have that. Then we have the internal validation, the most common type of internal validation. And by internal validation, I mean a quality measure where you don't need labels. And that is what we call the silhouette coefficient. That's very common. That you will see that basically in every paper that discusses clustering algorithms. I don't remember any paper with clustering that did not use silhouette coefficient. So this combines cohesion, so intra-cluster, and separation, intercluster. So it's both things at the same time. Clusters must be cohesive. So inside they must make sense. Like the points that are inside the cluster must be very strongly related to each other. But that's not all. They must also be separated from points that are not very related to them. So there you know, is a little bit like false positives and false negatives. You know, you can have points inside a cluster that don't fit that cluster, and you can have points outside the cluster that should be in the cluster. So both of them are a little bit like they kind of balance each other, and they, in a way, they both must be considered. If you consider just one or the other, then you're kind of only seeing half the picture. And what we do here, so this is a little bit more complex than the previous one. So you take a certain cluster, right? CK. You can do this for every cluster. then for every point in that cluster, xi, so xi belongs to ck, then you compute this ai, which is the average distance from xi to all other points of the same cluster. Basically, just take every other xj that also belongs to ck and just compute the distance to that. And this is just a way to represent the Euclidean distance, the norm of the difference of the vectors. Yeah. And then you divide by the number of points. So this is the cardinality of the set ck, which means basically exactly what I said here, average distance from xi to all other points of the same cluster. So that's ai. So that kind of represents cohesion, right? Because that has to be low. The distance, the average distance from a point to other points in the same cluster must be low. That's what we expect. Then comes bi. Bi is the average distance from xi to all points of the neighboring cluster. Now, what is a neighboring cluster? That's, I guess, the only like slightly ambiguous definition from the measure. A neighboring cluster is the cluster where that considering all other, so for example, here's what's happening here. For every m that's not k, basically for every other cluster, you compute the distance, the average distance between xj and all points from cm. Again, the same thing we did over here, but with m instead of k, so with other cluster. Then you do this for all clusters and you take the minimum one. The minimum one is the one that you consider as the neighboring cluster. So it's the cluster where where the average distance is the minimum one. Okay, so you can see that it's quite a heavyweight computing here, because you really have to compute basically from every point to every other point. So as usual, squared. And then thus the actual coefficient is this. So if ai is less than bi, which basically means that the average distance within the cluster is smaller than outside of the cluster, which it should be, right? You expect it to be, because if it's not, then it's kind of strange, right? It's strange that you would have a point where the average distance is larger inside the cluster than it is outside of the cluster. So maybe this could be like a border point. It could be a point that is so close to the border of a cluster and so close to the next cluster that comes on the other side of the outside of the cluster, that maybe it actually has it has smaller distance to the other cluster than to the actual cluster. For whatever reason, that could happen. Depends on how the clusters are being extracted. You know, when we think about a Gaussian cluster, so these blobs, this like roundish blobs, then that doesn't make much sense. But when you consider actual non-linear clusters, like the moons that fit on top of each other, then maybe a certain point on the tip of a moon may have maybe closer to the other moon than to the actual moon where it is located, because it's non-linear. So that's much harder to compute in that sense. But anyway, you expect it to be like this, and then you take 1 minus this thing, and then because if the top here is less than the bottom, then this is somewhere between 0 and 1, and then 1 minus that will give you something. So for example, if this thing is very, very small, then you will have something close to 1, and that's good. And I hope I got this right, because now I'm a bit good, but I think that's the case. So so then otherwise you have to invert this in order to, because the idea here is that you want something that goes like as close to 1 as possible. So if this is the opposite, then you have to invert this so that you get something close to 1. And this is an interesting way to visualize the silhouette coefficient So silhouette analysis for k-means clustering on sample data with 5 clusters. And these are the silhouette plot for the various clusters. So again, what we're doing here is basically we're just taking this idea here and just computing that for every point. So this is the data. So one cluster, cluster 1, cluster 2, cluster 3, cluster 4. Actually, okay, sorry. Cluster 0, cluster 1, cluster 2, cluster 3, and cluster 4. And then you take every point, group them by clusters on the y-axis here, and just compute the silhouette coefficient for all of them. So as you can see here that some of them have very low, very small silhouettes. Some of them has, because these guys are probably, sometimes it's even negative. It can be a little bit negative, like this. For example, the orange one is negative because some points are really badly positioned here. It's very hard to, like, probably around the border here. This is very hard to actually break something like this into clusters. If let's see, a question from Kumar. If the clusters are intersecting, then the B value is still same as clusters which are separated. Yeah, but the B value will be, well, if the clusters are intersecting and you have a point in the intersection, then it could be that the B will be much smaller than the A. I'm not sure I understand exactly what you mean, the question. The clusters are intersecting, then the B value is still the same as the clusters which are separated. Yeah, I'm not sure what you mean. But anyway, when you have clusters that are intersecting and you have points in the intersection like this, then the B will probably be quite small, and maybe smaller than the A, because then the neighboring cluster is very close. But I'm not sure exactly I understand. If you want to clarify, I think I can try to answer it.
Yeah, I was just trying to ask, like, this will not, A is still the measure within the cluster.
Yeah.
And the B value is still measuring between the two cluster. So I have a difficult to understand.
Yeah, I understand what you mean. Yes.
A and B will separate it.
Yeah, yes, because I understand what you mean. They are always separated. Yes, like you can never have A and B, because they will never consider the same cluster. Is that what you mean? Even if they are intersecting, yes, because by definition, A is the cluster that the point is in, and B is whatever is the neighboring cluster. So it doesn't matter if they're intersecting or not. And intersecting also is hard to define, because, for example, if you run k-means, there's never an actual intersection, because the clusters are all convex, so they never go on top of each other in a way. And also in the other cases, but in the other cases it depends what it means to intersect anyway. So if you, by intersecting, you mean that they're just really, really close to each other, touching, let's say they're touching each other, then yeah, it doesn't matter, because A and B are always different. A is always the actual cluster, and B is always the neighboring cluster. And then you can see, like, when you look at the visualization, it's I mean, you could just take an average silhouette value for each cluster, and already you will see that obviously the blue one here has much larger silhouette than everyone else, because it's much better separated than everyone else, right? Just so you understand, this line here is the actual, like, if you had to just have one coefficient, that would be it. Like, this is the silhouette coefficient of this clustering period, because this is the average of everything, of all the silhouette coefficients. And this is what you would give if you wanted to give one value, from final value. That would be the red line here, like 0.58, I guess, or something. But visualizing it is much more interesting, because then you see, okay, the blue one has much better results than everyone else. It's very separated. Then you take, for example, like the green and the black one, they are more or less like very similar, because they're actually quite well separated, but not super. So, and then it's interesting also to look at the shape. Then you can see that some points in this area here and some points in this area here are not that well. So there is like a small areas here where the silhouette is small or even negative down here, which means that in these cases, you know, probably the point that has this negative one here is like this point over here, because it's really in there. It's mixing up with the other, almost mixing up with the other clusters. So that should have a negative silhouette coefficient. And but by visualizing, you can see that, well, yeah, it's very good, but there are actually some areas over here where it's not very good. So that means that some points are actually in the border, are not super well defined. And then you take these two other guys here, the orange and these, like, whatever the color is, a teal or something. They are actually not that good. They are below the average, and you can see that they're very steep. So there's this steep curve, which means that some points kind of have a little bit of a good silhouette, probably those that are more separated away from the center or something like this. And then there's like very sharply decreases, and you have a bunch of points with very low silhouette. So that is basically what it means, is that there are some areas that are very confusing and not very well clustered, and even negative. So the negative ones here are probably the points that are kind of very, very much touching the teal one, the clustered, the number 2 here. Anyway, so I like this figure, because it shows you how you can have one value and then that's it, but you can also visualize it, and visualizing it gives you so much more information about it. But yeah, and then there is a comparison here that I added, which is, yeah, so this is scikit-learn, comes from scikit-learn. They have this nice comparison between many different clusters, and it's interesting to see some results. Like, for example, dbScan and meanshift are the only ones who actually realize that this whole thing is just one big cluster, because most of the other algorithms force the clusters to happen. So, for example, and they have to somehow find the clusters, period. And that's why you get some stuff like this. It's interesting, affinity propagation for some reason stuck with 4 clusters instead of 3. I'm not sure why. And then you see that most, if not all of them, will deal with Gaussian clusters like this. So blobs, roundish blobs. These are never a problem for any clustering algorithm. So if you're ever testing a clustering algorithm for real, you should never test with this data set here, because every clustering algorithm will work, period. It's like the easiest possible thing that you can do with clustering. But not if you have these other types of blobs. They are not only they're long or elongated, but they're also curved. So that becomes actually a bit harder for the clustering, as crazy as it looks. But it does, because then they're not just Gaussian anymore. And just in Gaussian data is just, I mean, they are Gaussian, but they're like distorted Gaussian. So it just becomes harder. I like also the results for spectral clustering for this one. They look very nice. Spectral clustering looks very nice in general. And dbScan did not do very well with this one, because these two guys here were mixed up. So you can take a look at this, and then this kind of gives you a big picture of how differently these clustering algorithms work, and where they're good and where they're not very good. Okay. Yeah, so never trust the first results that you get, because usually they're not very good. So try different parameters, try different distance measures, different techniques, etc., and just compare them to make the best possible informed decisions. Okay. That's it for the validation measures. And now, as a final thing, and as since one of the goals of the course is to give you some glimpse into the state of the art of clustering algorithms, I found it interesting to show you this paper. This is a published paper. Don't remember where it was published, but it must have been like 2 or 3 years ago. And some very nice, very interesting paper, very high quality paper. And it uses clustering for analyzing fashion across clothing and fashion across millions of images of people around the world and spanning several years. And clustering is like the method of analysis that they use with extra interpretation stuff. So I want to go through a little bit this paper and show you how they used clustering in order to do this research, which is quite interesting. And just to understand, like this is, for example, this is a cluster. Each of these sets of pictures are part of one cluster. And I guess just by looking at them, you can see more or less the similarities, right? So for example, these are women wearing red clothes. These are women wearing dark black clothes. These are people in general. I guess, I'm not sure, they're not all women. So people in general using these sports clothes and so on, right? You can look at each of these and see how they were, why, let's say, kind of like think about why they were put together. But actually what they did was, well, first of all, they extracted the clusters, right? And they used some very advanced clustering techniques, which I'm not really going to go into too much details here, because I think what is more interesting is to see how exactly they used it. Like, what do you get out of that after you do it, right? And the actual details about the exact clustering techniques and parameters and everything that they used, you guys can check on the paper later if you're interested. But basically they have these images. They analyzed the images and extracted these clothing styles from the images, and then they try to detect patterns by city and month, for example. The month of the year and the cities where these people are coming from. It's only the capitals of the world, if I'm not mistaken, like big capitals. And yeah, one thing that they did was, for example, to come up with this average person for each cluster, right? So you take a cluster and then you generate this average person, or this centroid of the cluster. That doesn't really mean anything exactly. Like it's not a person, of course, because it's the centroid and not like the medoid, which is the person closest to the center. So in order to augment that or to enhance that, they actually show the people closest to the centroid, which is quite interesting, right? So you have this artificial thing, you look at it and it's interesting to look also at this average person that doesn't exist, because you can see some interesting things. Like, for example, in this one, you can see that it looks like a woman with some kind of fancy headdress, and the clothes are maybe whitish, pinkish or something, not very well defined, but also not dark, some light clothes. So they're light clothes. It's a woman. It looks like she's laughing, or at least smiling, not laughing, at least smiling. And she has some kind of a fancy headdress, right? It's very blurry, but you kind of make a hypothesis. And then you actually go and say, okay, you know what, let me look at the people who are closest to the centroid, because I want to see actual real examples of this. And if you're closer to the centroid, then we kind of guess that you are representative of the data set. So that's an interesting way to analyze this also. And then you can see that, yes, these are women. They're mostly smiling. Not all of them are smiling, but they're mostly smiling. And they all have some kind of a fancy headdress, different ones. And they're all using slightly, let's say, light clothes. And then we have this little kid here. It's a little bit of an outlier. Also not a little kid here. So that's interesting, because you see it's not super homogeneous. It varies a lot, but still, so if you were to describe this cluster, you would describe it somehow like women smiling, using light clothes and headdress, and sometimes a kid. And then you can do the same thing for all of them. Like these is women who are covering their heads a little bit with some kind of. They're not all from the same culture for sure. They're from different cultures, I guess from different religions. But all of them are using some. I don't know the name, so I'm really sorry for that. But it's they're using these covers that are part of their culture and religion, but in different ways, right? And most of them are wearing dark clothes. So you can see that in average here, the clothes are dark, and they're also smiling. Apparently, most of them are smiling in these examples. So that's interesting. But again, this is just a very rough, blurry, example. And then you look at the actual people closest to Centroid. So what I like to show this is to give you ideas of what kind of analysis and what kind of methods you can use to analyze clusters after you actually got them, right? Because just getting the clusters is one thing. And then so on and so forth. This cluster here is people wearing yellow, or mostly guys, I guess, wearing yellow clothes, mostly from football teams. Like this is, I think, Colombia national team, and this is Borussia Dortmund. Also this one, I guess. There's a kid with a life jacket, yellow life jacket also. And there's a woman here with some kind of a yellow thing popping up. But mostly it's guys you're wearing some yellow clothes, as you can see also here. This I don't know exactly if this is I wouldn't say this looks perfectly like a man. Maybe it's a mix-up. But yeah, yellow shirts and so on and so forth. You can do the same for all of them. Now, one other thing that's interesting here is, okay, we look at the clusters, and now we're going to look at patterns by city and by month. And for example, if you look at this cluster here, so these patterns here that you see on the right-hand side, they are related to the actual clusters, right? So for example, if you look at this clusters here, they have, oh yeah, sorry, I forgot to say, these are style clusters with the lowest space-time entropy. So they computed this measure of entropy, and the ones that had the lowest one means that they have, in theory, the clearest patterns. They're farther away from being random, as we discussed before. Like, what's a pattern? Where one way to think of a pattern is that something is far away from being random, and these are the clusters that they chose with the lowest space-time entropy. So in theory, they are farther away from being random, right? They're the clearest ones. And this is interesting because this, for example, indicates the occurrence of these images throughout the year and throughout the world in different cities. And if you look at it, there's a very clear pattern here that this is Lagos. Okay, this is the city of Lagos. So most of the occurrence of this cluster here is in the city of Lagos. And it doesn't seem like there is a clear pattern throughout the year. So it's just like clothes that are used in Lagos throughout the entire year, period. And that's very interesting. Like this visualization here gives you a very interesting interpretation on the clusters. Then if we go to the next one, this is Cairo and Jakarta. This is Cairo, this is Jakarta, and this is Istanbul, the next one here. So this Istanbul is not super clear, but it's also quite strong. And then the rest of the places are not very strong. There's like an outlier here, which is Seoul in September, for some reason, who knows? Maybe Seoul in September has something happening there. But mostly these are clothes that are used throughout the year, mostly in Cairo and Jakarta. That's interesting pattern. Then this is, so here you see Bogota, of course. As I said, with the uniforms, I actually didn't. I did this before, but I had forgotten that. So it's good that the pattern was confirmed. So it's Bogota, and it's also and mostly in June. So I will guess. I'm not sure, but I will guess that that's when from June until like October of November, probably is when they play more like football championships there, or maybe that was a World Cup. this year. I don't remember exactly now. Maybe it was World Cup. So in June. Is the World Cup in June? I forgot now. I'm Brazilian. I forgot that. That's shameful. So, but yeah, you can see very clearly that people are using this in June, mostly, and then slightly more until like October, and then that's it. Maybe they're using it more in June because that's when the the World Cup starts, and then their team, I don't know, got out of the World Cup, so they weren't using that anymore so much. I don't know. That's open to interpretation. And then you keep going and you see another one again, more or less exactly the same as this one. So it's Cairo, Jakarta, and a little bit of Istanbul. But in this case, they're not using dark clothes. They're using like pinkish clothes, as you can see here. And this is one very interesting also cluster, because you can see that this one is basically like people wearing winter clothes, right? There's nothing specific about them, I guess, other than the fact that they're using dark winter clothes. The average here looks a little bit like a woman with a, cap, or whatever is the name of this, forgot now, cap or something, yeah. And then you can see that specifically very clearly that the patterns, although they happen all over the world, I mean, not exactly all over the world, because some of these places are more tropical places, and they don't get that code, but there's no specific place here. It's just everywhere. It's a little bit stronger in Berlin and Budapest, and maybe like this other place here, which I can't identify, unfortunately. I don't remember where it is. Paris a little bit. Anyway, and this is Kiev. So these places are a little bit stronger, but it kind of happens all over the world. But the most important thing is that it doesn't happen during summer. So if you take like June, July, August here, you see that it's very light here, because the patterns are not happening that much in these times of the year. They're happening more at the end of the year and at the beginning here. So yeah, so that's very interesting. It's space-time patterns. And then if you look at the clusters with the highest space-time entropy, so basically these are clusters where everything is almost random. So they're not far away from being random. They're actually very close from being random. Then you can see that it doesn't really matter. It's like it happens everywhere, all the time. And these are just some like people wearing dark clothes, period, or dark t-shirts, or people wearing blue shirts, or people wearing shirts with dark shirts with something in them. So you can see here in the average image that this is mostly, I would guess this is mostly like a guy with a black t-shirt with some kind of decoration, maybe like a band t-shirt or something like this. These, again, you can find them all the time, everywhere. People with striped or not striped, checkered shirts everywhere, all the time, and so on. So actually in this case, it's actually quite interesting, because we said that the interesting patterns were those that you're very far away from random, and that is one way to see it. But that, on the other hand, when you look at the clusters with the highest space-time entropy, even though they're very close to being random, it's also interesting to see what are them, right? Like, why are they very, very close to random in terms of space-time entropy? Because then you can see, well, these are actually patterns that happen all the time and everywhere. So so that is also a good insight to have from the cluster. And yeah, guys, that's it. Actually, what I wanted to show you. And you can see that it's very interesting. Like when you extract the clusters, extracting the clusters by themselves, that's not the end, right, of the analysis. You extract them, and then you somehow have to interpret them, or else, like, how would you make any decisions, right? There are pipelines, and that's perfectly fine if you do that. There are pipelines where you extract the clusters, you don't care about interpreting them specifically, and you just use that as a decision, as a way to base some other decision making of some other algorithm that will come after that somehow. You just say, okay, all I want to know is that we have 10 clusters. Like, just give me 10 clusters, and then I will do something with these 10 clusters. But I don't care what they are. All I care is that they are more related to each other than they are with the outside. That's also possible, but I like more. I mean, I like more these kinds of examples where you actually take the clusters after they're extracted, and you interpret them somehow. And these are the references. We have the course literature, we have the extra course literature, these are some interesting lecture slides also about DBScan from Dalhousie University in Canada. I recommend them also because they are just about DBScan, so maybe you want to take a look. Some lectures on clustering from Buffalo University in the United States. A review of clustering techniques and developments. This is quite, I mean, 3 years, it's not that old, it's quite recent. A big review of clustering techniques and state-of-the-art stuff. And I guess if you're interested in that, that should be interesting, just be cool to look at. And finally, the paper that we just explored, these street style, exploring worldwide clothing styles from millions of photos. And it's an archive, so it's free for you to get it from anywhere you want. And this was not a tutoring. This was half a lecture, half a discussion. Do you guys have any questions about anything specifically? Because if you don't, then we are 7 minutes ahead of schedule, so we can go for lunch a little bit early if you are hungry. All right, I will, well, if you don't have any specific questions. Elisa?
No, I don't have a question.
Oh, okay, I saw that you unmuted.
I'm still wondering about dynamic clustering that you said that maybe we can discuss later within the course, right?
Yeah, I told you that dynamic clustering, if you mean like clustering of time-dependent data, that is a bit advanced for this course specifically. I think I understand that it's important for you, and we can definitely discuss that. I think we should take that offline. Maybe you want to have a meeting between us to brainstorm a little bit and discuss that. Maybe I can bring you some references, but I think that specifically clustering time-dependent data, I'm not sure we are even gonna deal with that in this course because it's a bit more advanced. There is some content towards the end where we're gonna talk about streaming, and then we can talk a little bit about clustering of streaming data towards the end, but I cannot promise that we will go like super deep in that because, you know, I mean, the course itself is more like a little bit like an introduction, but it's not like advanced data mining, let's say. So in case that's something you're looking for your research, that could be something we could take up offline if you're interested. Like, we can brainstorm and talk a little bit just between us.
Yeah. Okay.
Right. And of course, if anyone else is interested in the same thing, then we can have like a specific meeting. But you know what, Lisa? Let's do it like this. Next week, on the tutoring, I will probably not go through content like I'm doing today. So then if we have half an hour, we can talk about that.
Yeah. Okay. Thank you.
Or if not next week, then maybe in the next one or at some point.
Thank you so much.
Okay.
Great.
Right, guys. So I will now let you go, and I will also get my lunch. So have a nice weekend. Thanks a lot for coming. I'm really, really impressed that you suffered through the whole thing, and see you next week.
Thank you. See you.
Have a good
Bye.
weekend. Bye.
Bye-bye.